Hello, it's Dr. Ron England here, and today we're getting into the good stuff. We're going to talk about regression analysis. And one of the things about regression analysis is we get to start looking at two variables and whether there's a correlation between those two variables. So what we're going to actually have is an independent variable and a dependent variable. So this is like looking at, does this cause this, or does this correlate to this? Because correlation is not causation. We're going to limit our cases right now to simple linear regression. So what does that mean? Well, the formula for the simple linear regression, I'm going to talk about the more advanced formula, but the formula is basically your y equals mx plus b. Your good old linear. Now, in statistics, we're looking at it as y equals beta naught plus beta 1 times x plus epsilon. What we're really talking about is there is a variable that actually does how much there is a shift in the y-intercept, which is your beta 1, or beta naught. It's got your slope of the curve, which is your beta 1, and then there's an error term. And this is really good for predictive analysis. So first things I'm going to do is start talking about some of the terms. Now, what I'm saying here is, let's say I have, let's say the weight of a car versus its mileage. That would be a good one. As a car weighs more, you would expect the mileage to go down. That wouldn't necessarily be a negative correlation, but it could probably be fit to a line, a curve. It may not be a straight line. There are other ones other than linear, but we're really just going to talk about linear. I've worked with all sorts of linear, nonlinear, or linearized equations in my work, but let's just get the basic one down. So the equation you're going to be dealing with is this y equals beta. First, think of y equals mx plus b, your standard formula that you have, but in the statistics, it's beta naught plus beta 1 times x plus epsilon, which is the error term. Now, we want to be able to visualize, and the last example isn't exactly no correlation. It's just very, very small correlation in it. But you can see there's the concept of a positive correlation, and the dots would be your observed values, and the line would be your curve fit values with the slope and the intercept for that. Negative correlation, basically, it's a negative slope. That's pretty straightforward. Notice in both situations that the r squared, which is a measure of how good it fits, is the same. I wanted to put this example up, with I have a 0.86 there, but these are just ones I stole off of plots that I was doing. I'm going to, by the way, give those to you. So an r squared of 0.89, you can see it kind of, and then the negative, which is still r squared of 0.86, is pretty much the same, but the line goes down. That's a negative correlation. So positive and negative correlation doesn't mean that they don't fit as well. It just means line goes up, line goes down. In no correlation, the line would be completely flat if there was absolutely none. Now, this is done through what's called the least squares estimation technique. And what you do is a calculation of predicted values. You first, and the way that is done is you are going to take the square of the residuals and you're going to minimize that. That's how you actually do the calculations. And it's a summation. It's a summation of that you're minimizing to get those predictions. I am actually not, and it may be shocking, but I'm not going to go into the prediction of that. You can look it up if you want to. What I want you to understand is that you're going to end up with two values, the beta naught and the beta 1, the slope and the intercept, which are predictions based on a minimizing the value between the actual value and the predicted value. That's how it's done, by minimizing the difference between the actual value of that you observed and the predicted value that you calculate by And that minimization is basically saying that the beta naught and the beta 1 that you get are calculated by minimizing the sum squared errors, which is the differences, sum squared, the sum of all of them squared between the prediction and the value that is actual. So formulas, I'm not sticking with this a whole lot, but it is a summation, and you can read the formula right there. You can easily look the formula up. You can actually relatively easily do this by hand. This is one of those great things that where a calculator, spreadsheet or Python becomes real handy, because there's usually a lot of calculations involved. But what are the parameters that you're predicting? Beta 1 and beta naught, or slope and intercept. I typically I typically do say slope and intercept, but when I say beta 1 and beta naught, it really actually is assuming that I'm talking about a statistical regression analysis. So what do you assume with regression? Well, first thing you got to assume in this specific regression that the relationship between X and Y is a linear relationship. Now, that actually is a little bit more complex than it sounds, because you know of linear as being mx plus b. It also can apply to formulas that can be linearized, that can be made into a linear format. So in other words, let's suppose that the log of both sides of y equals mx plus b. Well, is it still linear? It doesn't look like a line, but it can be linearized. And many of it, there's a lot of formats of equations that can be made into a linear format to estimate the beta naught and the beta 1, and then converted back into their other format. You're going to assume that the observations that you're using, all the pieces of data, are independent of each other. The homoscedasticity, which what a great word, homoscedasticity. And we're basically saying that the variance of the residuals, and the residuals are essentially the difference between the predicted and the actual value of y for every value of x, and that the variance is the same across all of those, and that those residuals actually are normally distributed. We're going to show some plots. Now, if you're doing multiple regression, you also have got to deal with multicollinearity, but we're going to talk about that in a future lecture, because we are going to do some simple multiple regressions where there's more than one independent variable, but there's one dependent variable. So there's more than one, there's x1, x2, x3, but there's only one y. So let's talk about this. If you were to take, and I'm going to jump back and forth. Let's go back to the plot. This plot right here, the positive correlation plot. Well, see it that you've got this line here, and you've got these values that are measured. The difference between, for any given x, between the line and the value would be the residual. Now, let's go plot those residuals. If you plot the residuals, they're going to look something like this. They're going to look like, basically like they're scattered, but there is a pattern there. So how can we detect that pattern? Well, we detect the pattern the same way we've always been detecting the pattern. This red line now looks like the average, okay? And really, the residuals should be, if you took the average of all the residuals, you should get 0. But if you take the frequency, if you do a histogram of the residuals, you're going to see that it looks very much like a normal distribution. In fact, predictively, it is a normal distribution. And then one of the other techniques, which is a QQ plot, which is really good for looking at this, is basically put all of these and put them in order. So what I mean by order is, the lowest, this one here, this guy right there would be this one here, and then just put them in order put an equal distance between each of them. Well, you can do it that way, but you can also do it based on, well, that's the easiest way. Let's not complicate. There's other ways to do this. And then plot them in order, just and look to see what that looks like. Okay, and it should look like a straight line. As you can see, in this specific scenario, as you get up into these higher values, it kind of differs from the line. Those are situations that you can that you sometimes do deal with, and we're not going to cover in this class some more complicated ways of dealing with values that are on both ends at the edge. And we're not going to actually give you data that looks like that either, which has very huge outliers or anything like that that you've got to deal with. We just want to kind of get into that basic theory of how to do a regression analysis and the techniques for looking at it. So realize that when you go from this beautiful right here, y equals mx plus b plot that really looks like it fits the value quite well with a relatively high r squared value, you can take those residuals and you can do quite a bit with this to look to see if they make sense, really, that the residuals fit a normal distribution and that they look good on a QQ plot. Now, what does that R squared mean? Well, if the data fit perfectly, the value would be 1. And if you had 2 observations and you did a least squares analysis of that to fit it to y equals mx plus b, you're going to get 1 every time with 2 values. That's because you just solved the equation for a line. That's all you just did. A fit of like 0.9 is a really good fit. Moderate fits about 0.5. Of course, the 0, it means that there's no fit. And basically what you're saying is that the model, this model that you have, the y equals beta naught plus beta 1 times x, doesn't explain any of the variability of the dependent variable, whereas the 1 says that it explains all of the variability of the dependent variable. Okay? Now, let's talk about this, because now you've got multiple parameters that define the data. You've got a beta naught, which is the intercept, and you got this beta 1, which is the slope of the line. So those are parameters. Those are predicted parameters. They specifically have well, I guess what I'm really trying to say is they're not precise. They're predicted parameters, which means that there is a level of error associated with the prediction. So how can you look at that error? Well, one of the ways is to look at the p-values. And one of the ways is look at the p-values of the residuals. So, but what you can do is you can calculate confidence intervals of the actual predictions across the line. We're going to do that. But really, you want to kind of be able to translate what these values actually mean. So let's see. Suppose we look at this example here, and the example, you got to really actually understand what the example says. In this example, the intercept represents 10,000 base cells when no advertising is done. So the slope in this, with this equation, means that for every dollar you spend on advertising, you actually get $5 in sales. By the way, don't confuse that with $5 in profit. It's $5 in sales. When you're doing this, and I've had somebody actually say that. Well, look, we're getting back $5 for every dollar that we spend on advertising. Yeah, you're making more money, but what's your margin? because if your margin is $1 and on a $5 sale and you're spending $1 on advertising, you're not getting anything back. You're getting more sales, but you're not actually getting a profit back. So don't make that mistake. But that's kind of a side thing here. And in this case, the R squared is 0.75. And the R squared is a relatively easy calculation, but you're going to be doing it with Python. You're going to actually ask for R squared values. What that means is that 75% of the variation in sales is explained by the model. And there's a low p-value in this if you calculate the p-value, which you're just going to do by asking that, I mean, you can do it by hand if you want to. And, it's a function inside of Python, so I'd say do that. But you need to know what it means. And if you have a low p-value, remember that low p-value typically means that the confidence is high. And in this case, it means that the relationship that we've actually got here from the data that we have has a high level of statistical significance. It does a good job. So that's good. So the coefficients. Sign. Positive means a positive correlation. Positive relationship. Negative means a negative relationship. Or it really just says the slope of it. The magnitude. So in this case, and it's easier to explain from back. So let's suppose this was 10. Well, what that would mean is that every dollar spent, the sales increase by $10 based on the model. Okay, so what we're really talking about is the magnitude of the relationship, the difference in the dependent variable with changes in the independent variable. Yeah, I definitely said that right. All right, now you can look at the significance with the p-value. You can calculate the p-value. And like in the case, let's say the p-value is 0.02. There's a 2% probability at 0.02, that's 2%, that the observed relationship would occur if there were no true relationship. Okay, it goes all the way back to the way that we were translating it before. So in the case of doing a hypothesis, if you were trying to use regression, which is, this would be looking at the null hypothesis, would simply be there is no relationship between the variables, okay, that the coefficient was essentially 0. That's, I'm not really going to make you do a lot of that. I'm really going to have you concentrate on your R squared values for this, because we're not going into depth into regression analysis, but we do want to be able to look at that and say whether there's a true relationship. That's one thing that you do need to be able to do. So remember, you're going back to that original equation, and the R squared is what we're going to use most of the time. So let's talk about that R squared. R squared equals 1 is a perfect fit. Okay. And you're typically going to see R squared values that range in that second caret, which is strong, 0.7, 0.9. And, if you get down to that R squared is 0, it's going to show, hey, it's not that great. Well, in that case, there's no fit whatsoever. It's 0. But sometimes you have weak fits and you're trying to look at it in a different way. And what I mean by a different way is actually trying to fit it to different forms of the equation. Because I've had many examples where it doesn't fit a standard linear very well, but it works out great if you modify the equations. And that's really what you want to do, is you want to be able to explain how the independent variable, what effect it has on the dependent variable. That's what the ultimate goal is. Now, you do have the ability to calculate standard errors and confidence intervals. So if you were to use, and I'm going to give you the code for this, I'm just not going to go over all this code in these lectures. They would get like insanely long. But in Python, you can actually do the calculation of the confidence interval. And this is just one that I had where I had a regression equation. You fit it. It's, the equation ends up being 1.95 times x plus 0.79. That explains your dependent variable. And then you can calculate and you can plot the 95% confidence intervals. So, and also the points that go with this. And you can explain, I mean, you can do a whole lot with this, but in this case, the R squared is 0.75. So it's not a horrid fit, but it's, you've got to make the decision when you're doing this as how useful is the fit itself. So the things that we're looking at, the assumptions, linearity, independence, homoscedasticity, normality, and that there's no multicollinearity. In this case, you don't have to really worry about the no multicollinearity because, well, it's not a multiple regression analysis, and that's where that would come into play. So let's say we want to do a prediction. Let's say years of experience versus salary. And you come out and you analyze and you find that that you get a coefficient that says $5,000 per year of experience is what people get. That'd be kind of nice if every year I got a $5,000 raise with every year of experience. That is a way of translating this, and you basically gather data and you look for it. Now, there's a few things that we want to be careful about. Practically, this is used everywhere. I don't even need to talk about business, healthcare, environment. I've used this more extensively than anything that I've ever done. But trying to find the correlation, and these are usually in causal relationships, but it's not necessarily causal relationships and correlation it doesn't mean if you see a correlation, it doesn't mean that there's causation. And even if without causation, there's still still identifying a relationship can be valuable. So don't just say, oh, well, that couldn't have caused that. This relationship means nothing. So right there, correlation is the things you look at. Okay, doesn't mean that one causes the other. Now, another one is this is within the range of data. In other words, if you've collected data for the independent variable in a certain range, it doesn't predict outside of that range. Because the one thing that you can do is if you've got an equation, guess what? You can throw in values that you've never observed. Outliers have a massive effect on regression analysis. So you've got to really look at, do those belong? And that is kind of a big deal. Like one outlier in regression analysis, you can have fit perfectly, and then there's just one value that's just out there, and you're like, what the heck? And I'm not going to say you can throw the outliers out. You can identify outliers. There's equations that identify points as an outlier. But does that point need to be there? Is the point? And making sure that you actually look at those assumptions, which I, by the way, have covered 3 times now. So I'm not going to go over those again to know if this data is actually useful for doing a regression analysis. We're going to have a little bit of fun with the examples. I've got thousands of examples of using regression, but we're just going to we're not going to make you do 1,000. As I did this was a huge chunk of both my master's thesis and my PhD, and coming up with much more complex models for figuring out how to do predictive analysis, and regression was definitely part of that. So, what do you need to know? First, we did simple linear regression models. 2-variable form. Y equals beta naught plus beta 1 times x plus epsilon. Okay, epsilon being the residual. Beta naught's the intercept, beta 1 is the slope. That's what you're getting. That's when you're doing a regression analysis, you're calculating for beta naught and beta 1. The technique that you used is called least squares estimation, which is basically where you take all the differences between the observed and the predictions, you square them, and you minimize it. Which, how do you minimize something? You take the derivative, and that's actually how you do the calculation of the technique to do that. You do need to look at the assumptions. Linear, independent, homoscedastic, and normal, all of those. And then understand what the coefficients mean. What does beta naught mean? What does beta 1 mean? What does r squared mean? And what do the p-values mean? And actually, even beyond the interpretation skills of what those values mean, is being able to produce visualizations to show this, to prove it. And I mean, I should go backwards one time, just a little bit, to those plots that I gave you, the residuals, the histogram of the residuals, and the QQ plot are extremely valuable for you to do. And I'm not saying sit down by hand and calculate these. These are relatively straightforward, easy to plot, easy to do by taking the data and just saying to Python, hey, give me a histogram of this. You may actually have to do a few things like, the ranges inside the histogram, but it's not that hard to do those. And then looking at that and saying, well, that could pretty much be considered to be normally distributed. And if you wanted to prove it, you've got methods for that too, which, by the way, I'm not going to go through because we're already at 27 minutes. And I'm trying to keep this one I was trying to keep below 30. If you've got questions, you know how to get in touch with me. And I've covered what I want you to know out of this discussion. So that's the important stuff. Thank you very much. Good day.